I think he left it on the table there. Am I live? Good. My name is Harold Cook. I'm the Director of Software Engineering for Lightfleet Corporation, and I want to talk about a little bit today about our technology that we're working to bring to market, and really discuss how we're a little different in what we've done on the fabric in order to overcome a lot of the efficiency issues that you have with traditional software stack-based switching. I'm not going to go into a lot of gory detail because I think everybody in this room is pretty familiar with it. But in general, packets consist of control information and then a payload. And the control information, of course, has to be processed, and that's generally in a very large software stack somewhere in a switch. In most cases, or in many cases, that there's a lot of software lookups involved based on whatever headers are present on those packets. You have a lot of overhead that depend upon the type of packet, whether it's a unicast, a multicast, or a broadcast type packet. And then the configuration of the switch, whether it's configured for cut-through or whether you're talking about store and forward routing. One special case that we're particularly interested in is multicast. And in a software-based switch, that poses a special problem for a software-based switch because typically what happens is a multicast packet has come in. Even if the switch is configured for cut-through, that switch will switch it over to a store and forward. It goes out and accesses something like an IGMP multicast distribution list, and then it serially retransmits that packet to every port. And what you end up with is a lot of skew and jitter. So if you look at a delivery time of a packet across a number of systems, oops, wrong button. Here we go. These data points right here are indicative of the jitter that you typically get in a multicast transmission. And then the least squared fit line right here of all those data points has an increasing slope to the right, which is indicative of the skew that you typically get from a serial retransmission of a packet on a software-based switch. I'm also going to point out that in this particular test scenario, you'll notice that this data is centered right around 53.5 microseconds. And I can go into a lot more detail behind this chart if anybody wants to talk about it offline. But we'll see this again in just a little bit. One of the problems when you start talking about multicast and in general a lot of other network protocols is that you end up in a lot of congestive switch situations depending upon what's going on the fabric. And of course, the default action for a switch, if it's in a congestive situation, is to start throwing packets away. In which case, you end up in a situation where you've got to have protocols which are detecting that and, of course, recovering them and retransmitting and a bunch of other things. The other problem with a software-based switch is they pose and actually create some very interesting security problems. Now, there's been a lot of advances in this over the last several years, but they're still not perfect. You can get into a situation where you've got a denial of service. You typically see this more on edge routers as opposed to spine switches. You've got malicious code attacks. The Spectre and Meltdown issues are actually a problem in some of the switches because of the processors that they're running. And then you're also subject to man-in-the-middle or spoofed address attacks that are created by a lot of the protocols that we have in a typical fabric. So if you think about it, packets in a modern or a typical switch, software-based switch network today, packets have to carry everything that they need to carry for the fabric to figure out where that packets go. And all of those switches have to look at that. What we're doing is a completely different approach. And in that approach, what we do is we call it switchless networking. And I'll describe that in just a second. But basically what we're doing is we've come up with a protocol where we actually can route the packets using hardware routing that eliminate the need for a huge software stack in the switch. So what we're really doing is we're shifting the paradigm of networking from packets carrying everything that are necessary for the fabric to figure out where the packet goes to having the application define the needs in terms of its data types and then allowing the fabric to adapt to those needs and figure out how to fulfill those needs. So I want you to, think about this for just a minute. This is kind of where our target application is. If you think about a typical east-west type traffic situation where you have a number of servers that are working together to perform a function, you've got a basically what I like to call an enclosed application environment. Well, if you're working in that environment, why are we paying the overhead for the typical generalized network protocols and all of the headers and all of the information that goes along with that, and all of the overhead of the software and the switches to support it? So some of the examples, and some of these are a little bit unrealistic for us right now, but not beyond the realm of possibilities. HPC clusters, supercomputers, big data analytics clusters, where you have a defined set of machines which are performing a function. You have multi-host-based applications that are running over long periods, like market analysis and trading, inventory systems, building, microservice types of environments, and even going so far as to say that a storage network where you have a front side or back side of a storage array. And I've been working quite a bit on NVMe fabrics in this regard. So, oops, I skipped a slide here. So what the alternative is, and it's not running, oh well. A connection-oriented protocol where we provide deterministic packet routing at hardware speeds, reliable data transmission with zero lost packets. And that's a very key point. We do not lose packets in this fabric. And the way that we accomplish that is by hardware flow control. Yeah, now it'll run. This little animation on the right-hand side of the slide is a depiction of very high level how our fabric actually works. But the key thing about this is that everything that we do is inherently multicast, with unicast being a special case of multicast that we handle just as well as a multicast packet. All of our control logic is in this yellow box right here, and we can talk about the contents of that if you're really interested. But we basically, what we're doing is we're pulling out a port mask based on a group identifier. And with that, we're able to route those packets by doing a hardware table lookup rather than having to do it in software. And so as a result, we end up with an implementation that's very fast, very low latency, very high throughput, with zero jitter and skew. In terms of the software, everything we do is RMA, remote memory access. We go from user space to user space. We have a kernel bypass architecture in our software stack. We do have device drivers that actually maintain the environment, but none of the actual data reception or data transmission goes through the kernel. And what we're doing is we're working to support standard APIs and frameworks. So this connection-oriented protocol that I was talking about, basically what we do is we define what we call a group, and then any member of that group receives the transmissions from one of the hosts as a member of that group into any of the other members of that group. And again, it's user space to user space. Groups are dynamic so that systems can come and go as they need. And it's all basically defined by the application that's running. Our packet structure on the wire, we have a very simple packet structure. We have a small, in this case, it's an 8-byte flit on the fiber, which is what we call start of message, that has the group identifier in it. We have a payload somewhere between 0 and 2048 bytes, and then a small, what we call end of message, which has checksums and completion information. And again, this is all enabling that hardware lookup in what we call our DDM, or switch replacement, if you will. Everything that we do is inherently multicast. Data is moved to all ports simultaneously. There's no skew and no jitter in a multicast environment. We believe that, well, we all know that multicast was lost. True multicast was lost when we made the industry transition from bus-based Ethernet to star topologies. And there's a lot of really useful things that you can do with it. And there's a lot of research that are going into multicast right now. I've actually got references to a couple of papers here. One from 2012, and then there's a more recent paper. Cornell is doing some work on an environment that they call Derishow. And people are beginning, a lot of interest in the industry to bring multicast back. So I showed you this slide earlier. Again, in this particular test environment, this was centered around 53.5 microseconds with a lot of skew and jitter. Exactly the same code, with the only underlying difference is transmission through the TCP/IP stack, which I was using in this case. I changed that TCP/IP stack to our API, and this is what you end up with. This graph is centered around 4.5 microseconds. There is no skew and there is no jitter in this. The only time that you'll notice in these two data points over here on the very outside of this graph right here, there is a little bit of jitter, but this is due to the PTP Grandmaster clock that I was using that was actually running at somewhere between 20 and 50 nanoseconds of resolution. So that's the only thing that causes the jitter that you see in this chart. So what you end up with is an environment where you have no skew, no jitter, and you're about 12 times faster in a multicast operation. You want to hold it to the end, or you want to ask a question? Well, that's because of the Grandmaster clock that I was using. There was about 20 to 50 nanoseconds of jitter between the systems and the clock.
So you were not able to measure the jitter. There was jitter and you couldn't measure it.
Inherently, we know that there is no jitter, okay? The only time that you would have any jitter in this, well, there is no jitter. There could be potentially skew based on the laws of physics and the length of the fiber that's involved. But we know that there is no jitter in this.
I have never heard such a thing. I would not think that's credible. Because I have a solution deployed right now that has 2 nanoseconds jitter. And with your measurements, you wouldn't even be able to measure that difference.
Let's talk about it offline, Christoph. I'd love to hear more.
Yeah, and the time at 4.5 microseconds, that's not competitive.
That's user space to user space.
Yes.
Again, let's talk more. So the kernel bypass architecture, we're doing that because we're getting improved latency and throughput. Again, the user space to user space transfers with 0 copies. And the kernel drivers are used to initialize the hardware and manage the group subscription tables. Some of the frameworks and the APIs that we're actually looking at, of course, I think everyone heard me say this the other night, that I've just recently abandoned our verbs effort because of the InfiniBand support that's in that interface. So I'm actually going to start looking at libfabric, and we'll get something going. In big data analytics and Java environments, there's a lot of different frameworks, but we've been looking at Netty, if anyone's familiar with that. And then there's other messaging APIs that are out there in the world. Some of them are open source. In particular, Aaron. We've been working with the Aaron team to do an implementation. We actually have that running. But there's some others that I've been looking at, 29 West, Informatica, and of course, Derishow that I mentioned a few minutes ago. And then we do have a driver that sits on the bottom of the TCP/IP stack that emulates an Ethernet adapter, so you can actually run this just like an Ethernet adapter. In terms of persistent memory, I believe that this is an implementation that will actually get us a low latency, high throughput, reliable network for NVMe over Fabric. But now that we've abandoned the verbs implementation, we've got to go back and look at another way to do that. So a couple of these presentations that have been here just before me have been kind of interesting to me. We've also been looking at Gen Z. And in terms of Gen Z, actually running the Gen Z protocol natively on our architecture. And we believe that we can get a true multicast implementation into a 100 nanosecond window. And that's kind of an ongoing research project that we have at the moment. In terms of network security, we believe that this is actually far more secure because we don't have the software stack. All of the packets are encapsulated and unpackaged by hardware, so there's no place that anybody can get control of the actual packet. There's no way to spoof it. And denial of service attacks are not possible because of our flow control. If we have a system on the fabric that is noisy and attempting to block, to create a denial of service situation, we can actually shut them off. So in conclusion, we believe that by enabling hardware routing with a new protocol and supporting that with standard APIs and frameworks, that we actually have a network implementation that is compelling in some of its features and some of its capabilities. Thank you. Questions?
Yeah, I have one question. It's kind of in regard to what Christoph has mentioned. Is there anything inherent in the hardware or your architecture that is limiting you from going lower than your 4.5 microseconds? I mean, if you were basing it on faster gates in the silicon or whatever, would you be able to improve that?
Absolutely. Right now, we're implemented in an FPGA. We know that if once we get to an ASIC where we've got opportunities to get much faster gates, really 0 is about the limit of what we can do, or very close to 0. Yes?
Hi. What's your typical topology here? Because when you say that there's no congestion and you get deterministic latency on all the endpoints, that assumes no incast. So is there a specific topology that this is applicable to, and how would it work in a case where you do have multi-layered and you have inherent incast coming in? Because that would cause...
Sure. So the topology that we're running on right now is a very simple tree structure. We're looking at close, we're looking at 3D torus, and what we're looking for and counting on is the flow control to being able to detect that, those congestion situations and help to manage those. We actually believe that this is because of the way we have the buffering and in our switch replacement, that we're actually much slower to congest and will be faster to clear if we do get into a congestive situation than a traditional network.
Okay, and a second question regarding the Spectre and Meltdown attack surface. I mean, those are actually independent of any switching at all. I mean, you could be doing storage over your... They're
processors, so if somebody breaks into the switch and gets some malicious code into the switch, which is not beyond the realm of possibility. I mean, you have command consoles. I can sort of envision maybe some ways to get it in there other ways, but yeah, you're right. That's kind of an outlying case, but if you look at what some of the switch vendors are doing right now, they're very concerned about that.
So on the latency and the 4.5 microseconds, that was a broadcast, which is probably pretty good, even by InfiniBand standards, for how many ports was that? 30-something ports or 20-something ports?
That was one source going to 22 destinations.
Okay, so that's still probably pretty good. But but point to point, I guess my question is point to point the same latency as the multicast latency?
So the point to point latency, I've got a whole bunch of other marketing charts that I could show you on that. I'd be more than happy to sit down with you. In fact, I know you've seen them, Scott. But yeah, our unicast latency can be much lower than that.
Okay. All right. Thanks.
Okay. Thank you.